We have seen the method of successive approximations in the previous classes, like Adornment decomposition method or modified Adornment decomposition method. And before that, we have seen the approximation by this Newman series, wherein we get a series which converges for particular values of lambda. Now here we'll see some classical Fredholm theory. Classical Fredholm theory. Now what I'm going to discuss here is something like this. We consider this integral equation. Consider the Fredholm integral equation let us take this equation. Y of x is equals to fx plus lambda integral from a to b t x comma t y of t dt. Let us take this as equation number 1. Now for this integral equation 1, we have seen there is a power series, that is Newman series, and again we have discussed the convergence of Newman series. So we have seen that equation 1, this is that particular equation 1 has solution in the form of a uniformly convergent power series, uniformly convergent power series in parameter lambda, and then again you have seen that mod of lambda is less than beta and those things. Let me write here for table value of mod lambda. Now here we will consider a method in which this will hold for general lambda. So now we consider general form which is valid for all values of the parameter lambda. Right now, for this, let us suppose that our kernel kxt, suppose that kernel k x comma t is integrable function over a comma b. That means we can integrate this kernel kxt over the integral a comma b with respect to both the variables x and t. Now what we do is divide the interval, this a comma b, divide the interval a comma b So we divide this interval a comma b into n equal parts. So we have this a comma b. We are dividing this into n equal parts. So let us take that to be say x1. Let's take this a as x1, then 2 equal. This is very important, equal parts. So x3, x4, x, and let us take this last as xn. And previously xn minus 1. And similarly, I can denote this x1 as with respect to this t. So x1 is equals to t1. Minute here. Only x1 is equals to t1, x2 is equals to t2, and this is t3. This is tn. And let us take this distance to be h. And then if you want to find what is h, the total distance is b minus a, and then you are dividing throughout by n, dividing this interval into n equal parts. So I can write h is equals to b a divided by n. This is your observation. Okay? So let us write that. So this is equals to. So we are dividing into n equal parts. X1 is equals to t1, and that is same as a. Then we have taken that x2 is equals to t2, and then to a you are adding h, and h we have already stated that h is nothing but b minus a upon n. Likewise, our xn will be equals to tn, and that is nothing but a plus, we can see x2 is a plus h, x3 will be a plus 2h. That means we are adding that distance 2 times, so this will be n minus 1 times, and definitely that will be equals to op. And here I can see where h is equals to b minus a upon n. So for this, let us use some approximation. So by using approximate formula, so already that interval you have divided into n equal parts, and then you are taking the integral over this interval k comma t I of t dt. That means you are taking that integral from a to b, and then you have divided this a to b into n equal parts from t1 to t2, t2 to t3, and so on. So this integral can be converted into this n equal integrals, and then you can have the approximate things. So let us write this approximately, that h will be there. Let me write this h summation j from 1 to n, k, x is there, and then I'm approximating that using t. So y t at kx comma tj, y at tj, and then this j is from 1 to n. So using this expression for integral kx t y t dt, our equation 1 will become, therefore our equation 1 becomes y of x is equals to fx plus lambda, and h, you take that h outside, and then that integral will be shifted or replaced by the summation j from 1 to n, k comma tj, y at tj. These are approximations, very important. And then again we have divided that particular interval a comma b using xi's. So at particular values of xi, say at xi, y at xi will be equals to, replace your x by xi. So f at xi plus lambda h summation j from 1 to n k x comma tj, and this x is replaced by xi, so xi comma tj y at tj. Let us take this equation 2, right? And if we denote y at xi to be yi and f at xi to be fi, k at xi comma tj as kij, and this is y at tj is yj, so you can write this as yi is equals to fi plus lambda h summation j from 1 to n t I j yj. Let us take this as equation star. So we denote here y at xi to be yi, f at xi to be fi, lambda h are here, and this k of xi comma tj is kij. If you want, we can write here where yi is equals to fi is equals to, and kij, let me write this only one, k at xi comma tj. Y at xi is nothing, y at xi is nothing but yi, so this is y at xi and this is f at xi. And this xi and tj values you know, because um, you are dividing the interval into that n equal parts, and then we are writing those points as x1 x2 up to xn and y1 y2 up to, sorry, t1 t2 up to tn. So if you see here equation star, there are n equations and n unknowns, where fi is the values you know, kij you can find, so the unknowns are yi's. So the star is the system of n equations in n unknowns yi, right? So this star, let me write what is I here. I from 1 to up to n. So for each I there is one equation, so there are total n, there is xi, so there will be n equations. And equations 2, this expression in equation 2 will give you the approximate solution for your integral equation at the point xi. Let's write that. Equation 2 or equation 2 or expression in the equation 2, we are writing equation 2 gives approximate solution to integral equation 1 at points 1 comma x2 xn. So we will get the approximate solution for your integral equation. Now we can use interpolation. So yi given by 2. So for each xi you will get some yi equation here, and you can use interpolation. So yi given by equation 2 can be plotted and using interpolation. If you don't know, then check what is interpolation. Using interpolation, is something called as interpolation and extrapolation. Interpolation curve y of x can be obtained which is the graph of solution of your integral equation 1. Solution of equation 1. So we have approximated it by using these values. We have divided your interval into n equal parts, and of course as you increase your n, the intervals will be smaller and you will get better approximations, right? So if you see this star, if you see this equation star, there are n equations in n unknowns, and we can find the coefficients matrix of those equations. So that matrix, and we can discuss about the solution of that too. So note that the coefficients of some star is given by, you can check this, you can verify this very easily. We have 1 minus lambda h k11 minus lambda h k12, likewise we have minus lambda h k1n. Here you have minus lambda h k1, 1 minus lambda h k22 minus lambda h k2n, and last row will be minus lambda h kn1 minus lambda h kn2, 1 minus lambda h kn. This you can easily verify. You write the system of n equations in n unknowns given by the star, then you write the coefficients of yi's as a matrix, and this is your determinant. Okay? So let us denote this by we have denoted earlier by d lambda, and here as the value of n increases or decreases our determinant values, that order will change. So let us write this as d and d suffix n lambda, right? And obviously if this dn lambda is not equals to 0, the system in star will have unique solution, and it will be equals to, if it is equals to 0, then we'll have approximate eigenvalues of those kernels. So system star has unique solution provided for d suffix n lambda is not equals to 0, while if your dn suffix lambda, sorry, d suffix n lambda is equals to 0, we will have, or we will give approximate eigenvalues of the kernel, right? On this we will see one example to see how to get the d and lambda and how to get those eigenvalues. So let's write this example. Let's take this y of x is equals to lambda integral from 0 to pi sin of plus t y of t dt. Now here if you see whether interval a comma b is nothing but is 0 to pi. So homogeneous. If you take n is equals to 3, say you can check with n is equals to 4, 5, 6. Taking n equals to 3, we get our value of h, which is h is equals to b minus a upon n, and in this case it will be pi minus 0 upon 3, so pi divided by 3, and hence if we change that x1 x2 or s1 s2 the values, we will have x1 is equals to t1 and that will be 0, that is a. Then x2 is equals to t2 and that will be a plus h, that is 0 plus pi by 3, and x3 is equals to t3, that is plus pi by 3, so 2 pi by 3, right? I guess I made some error down the line here. I said this is equals to b, but it's not equals to b. This is x, this b will be here, so this is xn will be here, and this will be xn minus 1. Right here. Okay. Because in that case, am I correct? Yeah, in our case, then x3 should be equals to pi, but in our case here it should be x4 is equals to pi. So make the respective changes in the previous things, or you can start with x0 and then you'll have xn, that is x3 is equals to b. That can be done. So do the respective changes, right? So x1 is 0, x2 is pi by 3, x3 is 2 pi by 3. So our interval will be like this. So this is our 0, this will be pi by 3, 2 pi by 3, and then here we'll have 3 pi by 3, that is nothing but pi. Now in this example, our kernel kxt, kernel kx comma t is nothing but sine of x comma x plus t, right? So you can verify these values. I will write for you. You'll get k11 is equals to 0, get k21 is equals to 0 0.866 1 2 3, k31 you will get this as 0. Again 866, you will get k12 as 0.866. These values you verify. k22 is 0.866, k32 is 0, k13 is equals to 0.866. These all values you can easily check. k23 is 0 and k33 is not wrong, minus 0.866. So this you know already that kij is nothing but this approximations what we have done. Kij is nothing but k at xi comma tj, and this xi and tj values we already know, and again our kernel in our example here is sine of x plus t. So you put the approximate values, you put the appropriate values in that sine function. You can use a calculator and you'll get these values. And if you want to write this dn, in our case it is d3 lambda will be determinant. Again you verify this very easily. 1 is minus 0 correct. Yeah, h is also there. The value of h is pi by 3. So all those values you substitute. Lambda is there. So minus 0.907 lambda minus 0.907 lambda. Here it is minus 0.907 again lambda. 1 minus lambda into 0.907. This will be 0. Then minus 0.907 again lambda. This is 0 and this is minus minus plus becomes, so 1 plus lambda into 0.907 and determinant value. We can evaluate this determinant, and you want to find the approximate eigenvalues. We put that dn lambda, that is d3 lambda is equals to 0. This will imply when you find the evaluate that this one determinant, you will get 1 minus 3 0.097907 square lambda square is equals to 0, and from here your approximate eigenvalues are plus or minus 0.6365. So likewise you can find eigenvalues, and again you can find the solution, and you can get the approximate solution for your integral equation 1. So briefly to say, we have seen the classical theory wherein much classification is classical Fredholm theory. So we have seen this method for approximation which will work for all the values of lambda. In the next videos, the next Google Meets or in the next meetings, we will see Fredholm's first theorem, and we will see how to solve some particular integral equations by using Fredholm's first theorem.